I don't know, 30 to 40 minutes, I think, to do this. So not too bad. All right. In our textbooks, Infinite Wisdom, they're doing everything backwards like usual. So here we're talking about area under curves. Typically, you present this before you start doing integration, but whatevs. So let's take, for example, we want to do the integral from 0 to 3 of 30 dx. What is the antiderivative for 30?
That would be 10 to the...
No.
Not even close.
It'd be 30.
I forgot the formula.
What? I don't even know what it is.
Wait, so just the antiderivative of 30?
Yeah.
It would be, hold on. It would be... I forgot the formula. What was it? It's plus 1 something.
No. I got it. It's over the, and then the chat.
Is it over?
Chat.
It'd just be 30.
It's X.
It'd be X to 30.
X squared.
No, am I stupid?
You guys are all bad right now.
I forgot.
Wait a minute.
I forgot the normal one.
30. Oh, I know.
Oh, because the one just go.
I didn't hear anybody say that.
No, I didn't, but because the one will just come down and no X. And, wow, so that's bad.
What is it again? It's like divided by something.
So the formula for our antiderivative is this guy right here.
What formula did you use those? Or should we memorize that? I mean,
It'll be on the equation sheet. But like, you should, I think if you're going to use it enough that it'll just be memorized. You know what I mean?
Alright, let's do it, guys.
Okay. Sam, you happy? Okay.
So 30 would just be 30.
X to the 0.
Actually, 0 is
So,
So it's already divided by 1. It's 0 plus 1.
yes. You got it. So, when we do the definite integral, then we just evaluate it at 3 and 0, and we get like 90, right?
I do agree with that.
So if we think about this graphically, the graph of y equals 30 is just like this horizontal line, right? And if I go from 0 to 30, that area is like a height of 30, width of 30 rectangle. So that's 90 also. It turns out that the definite integral and the area under the curve are equivalent. They're going to find the same thing. Okay? So that's the example. So let's do a couple here of example problems doing this same idea. So it's asking us to start by drawing a sketch of the function. Yep. Then use geometry to find the area, and then use the definite integral to find the same area. So graph f of x is equal to 3 from 1 to 5. So that's our area. So our area will just be length times width, or length times height. So we get 12. So if I wanted to integrate the same thing,
What is that? 3dx.
3dx, yep. I get the same result. Okay, let's do another. So the next one is 2x. I think it was from 0 to 3. So if I plot this, it's over 1 up 2, over 1 up 2, over 1 up 2. So there's y equals 2x. If we're going from 0 to 3, that's my shaded region. What shape is that?
That is a right triangle.
Great. What's the area formula for a triangle?
Is 1/2 the base height.
Okay. So the base here is 3 and the height is 6. So we get 9. If I want to do the integral of that same thing from 0 to 2, the antiderivative of 2x is just going to be x squared. Again, we get 9. Everybody feeling pretty good on what we're doing here? The really neat part about doing this, though, is if we want to do one like D. Notice this guy, not something that we know how to integrate by hand, right?
Use that GDC. Oh, that.
Yeah, but we can also do this just geometrically. So if I graph this thing, it's going to look kind of like that. What shape does that look like?
That's a parabola.
No, from an area standpoint.
Oh,
Not a circle,
a semicircle.
half a circle,
A semicircle.
right? So what's the area formula for a circle?
1/2 pi r squared.
Pi r squared, since it's a half a circle.
Then you add half. Semicircle.
So the radius, the center would be at the origin here. The radius would just be 2. Semicircle would be a great description of this. So we just get 2 pi for our answer, right? Yeah, so now if we want to do the integral of that, as suggested earlier, can't do this by hand. We don't have the method or know a method to do this by hand. And in fact, the method to do it by hand is way complicated. Maria, we haven't even talked about the method on how to do something like that. It's on the to-do list for next class, though, so we're going to see it. So, Maria, I'm going to expect you to do this one by hand on the test. Yeah, exactly. So we'll just type into the old calculator. So I just type it in and press enter and give it a second to think. It gives me that decimal. Do you think that's the same as 2 pi? Let's check.
3.1415.
Woo! Yeah. What do you guys think? Pretty good? The other kind of problem that you can be asked to do is to find the area enclosed by 2 curves in the x-axis. So I'm going to just start by graphing this to get a picture. So I'll go to my calculator. And just type these 2 guys in as separate functions. And I'm going to pick an appropriate window here. So like the smallest value of x this function can have is -3, because anything less than that is going to give me a square root of a negative. So I'll take my x min at 0 or at -4. Everybody cool with that? This guy is going to cross the x-axis at 2, and then it's going to be above the x-axis beforehand because it's the negative sign in front. So probably just a little bit past 2 will be fine. So I'll do to 3 maybe. since we're going above the x-axis, -1 is good for my y-min. And then, I don't know here, if I go all the way out to +3, 3 plus 3 is 6, square root of 6 is a little bit less than, will be less than the square root of 9, right? Which is just 3, so maybe I'll do 3 as an x max, or y max. And then I'll just hit graph and take a look. So there's my first function. There's my second function. So I'm looking at this area enclosed by the two curves and the x-axis. So I'm looking for that area. So if I think about it, well, up to here, that's just the area under the first curve, right?
Yeah.
And after this point, that's just the area under the second curve, right? So what I really need is just this intersection, because I can say like the integral from -3 to whatever of, well, I'll just write it as g of x, oh, sorry, f of x dx, plus the integral from where that spot to 2, g of x dx is going to be our area, right?
Okay.
So to find that intersection, I could do it by hand, but nuts to that, I'm going to use my calculator. Pick the intersect command, enter, enter, enter. The intersection is at 1. And then it's just calculator time. So to do this, do math, fn int, -3 to 1. Now I've already typed in f of x into my calculator in the y1 spot. So I could type it in again, or what I would prefer to do is just do, yeah, vars, yvars function y1, and then just do the same thing here, 1 to 2, and I'm going to use y2 dx and press enter, and I get about 7.45. What do you guys think?
You said ALK, and I think it was ALK at first.
Yeah, I think I forgot the C.
You need to drink after you do these math problems.
All right, let's take another example. So here's like kind of a story problem. It says a ramp for a skateboard has a side piece that is modeled by the area enclosed by the y-axis, the x-axis, the function y equals 1, and the curve g of x equals yada, 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 with all measurements in meters. Okay, sketch, use the GDC to sketch a piece. Okay, well, that's fine. All right, so since the y-axis is one of my boundaries, I don't really need any negative x's, right? And this guy hits this, has a 0 when x is equal to 6, right? Because 6 minus 3 is 3, 3 squared is 9, 9 minus 9 is 0. So I'll make my x max a little bit bigger than 6, maybe just 7 or something. Is that okay? All right. Since the x-axis is one of my boundaries, I'll use -1 as a y-min. And then like the roof of this is going to be 1. So I can just do like 2 for a y max or something. Henry, what's up?
Is it really worth it to go in and do this, or is this the way you like to do it? I just normally graph it and then I just do
Yeah, you can do whatever you want. I just like using my common sense to get a good window so I don't have to go back and forth and back and forth and back and forth. I just get it like it's a one-shot deal for me.
Yeah.
You know what I mean?
Oh, yeah.
All right. So I'll do that and I'll hit graph. Oops, I didn't type my functions in. Stop, stop, stop. So we'll type in 1 and then our other one, 3 minus square root 9 minus x minus 3 squared. Again, another one that we have no clue how to integrate, but that's okay. The calculator will handle this for us. Again, even Maria doesn't know how to do it yet.
Not even the techniques.
but she will soon. Give her a couple days. All right. So if I look at this, this is the shape that I'm interested in, is like this section right here.
Oh, yes.
Right? That's bounded by the x-axis, y-axis, and then those two curves. You guys good with that? All right. So if I look at this, this section is just the area under y equals 1. And then this section is just the area under the other curve. So I just need to find this intersection and break it into two integrals, just like we did the last time, right? So again, we'll have the integral from 0 to whatever of f of x dx plus the integral from whatever to 3, right? Was that what it was? Yeah. So 3 g of x dx. We just need to find that value, which is just the intersection of the two curves. So second trace, intersect command, enter. And then for a guess, I probably have to move it closer because there's two intersections. I want to make sure I get the one I'm interested in.
Yeah.
So 0.764. So that's our answer for part B. And then to find our answer for part C, I just now type the thing in and watch this. I'm just going to recopy the last problem and just update the bounds
Wow.
because I got it all set up. I just need to change the bounds of integration because I typed f of x into y1 still and g of x into y2. So like it's all set up for me. That's a nice little time saver there. And I get 3 for that. What do you guys feel? It's all right? No big deal, right? What's up?
Nothing, I'm just tired.
Oh, okay.
What did you say? Oh, hi.
All right. So again, in true backwards fashion, the next section we're going to talk about approximating areas under the curve. So what if we were to have a function where we're not given an equation, or even a complete graph, but just given like points for the function? Now we're not going to be able to calculate the area under it exactly. Yes,
Can we go back there?
sure. But what we can do is we can create an approximation for this. So if I just think about this as like, so say we have this data table and I plot the data into the scatter plot. If I just think about this as like a bunch of linear functions that are kind of hooked together, what I can make is I can divide this into 4 trapezoids. So remember the area formula for a trapezoid from geometry would have been this.
Oh, I do not remember that.
So like this side is B1, that side would be 2, and that piece is the height. So T1, the area is going to be 1/2 12 plus 17 times the difference in the x's, so 2. Does everybody feel okay about where I'm pulling my numbers from?
I see it's the heights.
Yeah, the heights are just the difference in the x's. They're 2 the whole way through. I didn't look at all the problems in the textbook, but that's pretty typical. So we'll just add up those 4 areas and that'll be the whole thing, right? Now I'm going to notice something here before I go to my calculator. Look at this, times 2 and times 1/2. Those will just cancel those guys out. Boy, that makes life a lot easier. And additionally, I noticed that, hey, I'm going to have 17 twice, 18 twice, and 16 twice. And just 12 and 15 once each. So to type this into my calculator, do 12 plus 2 times 17 plus 2 times 18 plus 2 times 16 plus 15. And 129 is my answer. And because this was in thousands, I'll say it's 129,000 meters cubed. I guess this is some flow through like a pipe or something. Or maybe a river, who knows? That'd be a big stinking pipe. What do you guys say here? So the whole idea here is we're just going to take our curve and like geometry it up into chunks and then add up the geometric figures. Okay, so let's do another one. It says here to use the trapezoid rule to find the value of, textbook has a typo to go along with the example, so that should be a 4, not an 8 there. Using trapeziums, that's the international way of saying trapezoid. Yeah, that are 0.8 units wide. So for the first trapezoid, that'll go from 0 to 0.8. Trapezoid 2 will go from 0.8 to 1.6. The third one will go from 1.6 to 2.4. The fourth one will go from 2.4 to 3.2. And the fifth one will go from 3.2 to 4. Everybody feel okay there? So T1 is going to be 1/2 times, let's call f of x this guy. And I'm just going to write this as f of 0 plus f of 0.8. And then the height will be 0.8 for all of these, right? So I'm just going to go ahead and grind through this. Is everybody okay with where I'm pulling the numbers from?
Absolutely. Yeah.
Okay. So that's that, right?
How many others?
Well, that's what I figured out at first. Because it wanted to go, oops.
Wow.
Don't do that. Because it's going from 0 to 4.
Gotcha.
So I wanted to make 0 to 4. Needed 5 trapeziums to do that. Feel good? So to get this into my calculator now, again, I'm going to observe that, well, each one of these has this 1/2 times 0.8. So I'm going to just like kind of pull that out front. Everybody's good? And then inside, I'm going to have 2 of each of these. And then just 1 of this one and 1 of this one, right? So I'm going to have f of 0 plus 2 times f of 0.8 plus f of 1.6 plus f of 2.4 plus f of 3.2 and then plus f of 4. Is everybody okay with that? And now I could compute each one of these separately and then have to copy it into my calculator, but that stinks. Instead, what I'm going to do is I'm just going to go ahead and type in this into y1 and just use my calculator to call that value. So to get the absolute values, I press math and then go over to the num and pick ABS. That's the first one. And then we'll just do 2 to the x minus 8. Again, something we have no clue how to integrate this by hand. And I'll do 1/2 times 0.8 times the quantity y1 of 0 plus 2 times the quantity y1 of 0.8 plus y1 of 1.6 plus y1 of 2.4 plus y1 of 3.2, and then close that quantity plus y1 of 4. And then close that quantity. And I get about 18.1. And if I wanted to, I could find the exact value to compare just to make sure I'm not like bonkersly far off, right? Because I can just type this integral into my calculator and just have it do it for me exactly. And again, I typed the function into y1, so I'm just going to use y1 rather than typing it in again. And I should get something that's fairly close, I do. So I have a little bit of an overestimate with my trapezoids, but that's fine. We knew it was approximation anyway. Pretty decent, right? If I didn't have a calculator to use, boy, that'd be pretty good. My last example here says we have a velocity time graph, shows a train journey. Use the trapezoid rule to calculate the total distance traveled by the train. We're not really going to use just the trapezoid rule here, though, folks. I would just kind of chunk this geometrically. So I'd say, okay, well, there's a triangle. There's a rectangle. That's a trapezoid. That's another trapezoid.
Rectangle.
That's a rectangle. And then there's a triangle.
So, wait. Sorry. I'll say this before you answer. So would you do the trapezoid? What's it called, the trapezoid theorem? What's it called, trapezoid? You do the trapezoid thing with only the trapezoids, and then you just.
Yeah, I'm just going to calculate the area of each of these 6 things and add them up. So like the triangle is 1/2 base times height, right? So the base here, if this is 1 and that's 2, that's 0.2. And the height is 80. And then the rectangle is 0.4. And its height is 80. The trapezoid is going to be 80 plus 60 plus 0.2. The other trapezoid is going to be 60 plus 100 times 0.2. The next rectangle is going to be 100 times 0.6. And then my last triangle is going to be 1/2 0.4 times 100. And then I'm just adding it up. It's calculator time.
Punch it all in.
What do you think? Yeah, it's not too bad, right? This is, conceptually, it's a new idea, but like the execution of actually computing these things is really pretty easy. You're just talking about like some super simple geometry, like finding areas of like simple figures, stuff that you would have done in middle school. You just have like a different application for it here, which is fine. Like, okay, easy enough. Like integral, kind of a complicated idea, but the geometric interpretation, pretty simple. The geometric formulas that we're going to be asking to do are pretty simple. So like we should feel pretty decent about that. So I type that and I get 140. And then I guess this is, since the graph is given in kilometers per hour, when we we accumulate that, the unit is just kilometers, right?
Yeah.
Everybody feel pretty decent about what we've done here today?
I like the second
Yeah, it's fairly straightforward, right? We're just like doing areas and adding them up.
part. I can do that all day long.
Perfect.
Do you like to integrate or differentiate?
Well, I will tell you this, like, from a beginning student standpoint, integration is usually easier than differentiation. In a reality standpoint, integration is much more difficult, so much so that there are simple problems that are just not integrable. Like there is no formula for anti-differentiation. After learning a dozen or so rules for differentiation, you can essentially differentiate anything with just like some elementary rules, and it's easy. I mean, it can be computationally difficult, but conceptually it's pretty easy. It's not that way in practice for integration. So much so that there's like a whole branch of mathematics devoted to just like, how do I simulate or approximate this integral? Used very frequently in statistics because it's talking about probability. Remember we talked about probabilities being like the area under the distribution curve? That's what you're doing. And some, particularly if you're doing Bayesian statistics, you're going to be left with integrals that are not like there's no formula to do them. So you simulate the integral with like a method called Markov chain Monte Carlo, which like is a way to simulate the solution to an integral problem, which sounds terrible. It's not that bad. You have to use a computer though to do it. Like the computation is just like too cumbersome to do by hand. So in practice, integration much harder. I'd rather do differentiation because I know I can do it by hand or with a simple calculator at worst case scenario, like even if it's terrible and complicated. Integration, I do not have that luxury. Some of them can be, just not possible to do by hand. So your quiz description, and that's going to be next class. I'm going to ask you to find general antiderivatives. When I say general antiderivative, what do you need to make sure you include? The plus c at the end.
Yes.
Remember, you got to have a plus c.
So when you
Because if you take the derivative of like 3x plus 5, the 5 just disintegrates, right, Sam? So if you tried to do the antiderivative of 3, you don't know what the constant at the end would have been.
Right.
There could have been one. Maybe it was nothing. Maybe it's 7. Maybe it's 12. Maybe it's 19. But you would have never, there's no way to know. Unless you're given a boundary condition. That's the second bullet point. So find the specific antiderivative given a boundary condition. So if I tell you, like, what's the antiderivative of f prime is equal to 7, when f of 1 is equal to 10, then you know that I can plug 1 in for x and 7 in for f of x and solve for c. So, yeah. You should be able to evaluate definite integrals both by hand and with a calculator. Okay. And then be able to do integration story problems, like giving it, like in a situation where you're given a rate function, calculate the accumulation. So I think we did 2 pretty decent examples of this in the notes. So like this 11.5 example is a good one. And then we had another one here. This 11.8 example would be a good one to look at. Will resemble kind of one of those sorts of problems. Next class. And then your test description is here also. So it's basically the same thing plus being able to do these area kind of problems.
You said we're doing the same thing that we did like this test where it's quiz, the data review test, or is it just quiz test?
I think let's talk after the quiz day, see how you guys feel about the quiz, and we'll decide whether we'll do the test on Monday or not. I prefer to just do it on Monday, and regardless, Olivia, if you just want to, if we aren't doing it on Monday, if you just wanted to go to study hall and do it on Monday, and like, you know, like, yeah, so like if you guys, regardless of what we decide to do as a class, if you want to take it on Monday still, I can just dump the things in the study hall room and you can go down and take it on Monday, even if we're doing a review day, everyone else feels like they need to do that. That's fine if that's what you want to do. Totally your option. Whether you want to do it before or after, I don't care.
What is that to,
No, it's not, the test is on Monday.
can you look at next